Here is a question that I would like us to keep in mind as we go through the contents of this video. Linear regression is which of the following? Is it a machine learning algorithm, a representation learning algorithm, a deep learning algorithm, or none of the above? We now have a decent understanding of the fundamentals of TensorFlow. Let's dig a little deeper. Let's take a look at how TensorFlow can be used to actually build a machine learning model. Here we will work through the logic of a specific machine learning problem. We'll start with linear regression, which is really simple, and see how the TensorFlow approach to regression is pretty different from other cookie cutter approaches available in Python or R. We will also understand the ideas of placeholders, feed dictionaries, and variables. We'll run programs with different inputs making use of these concepts, and then get to the really crucial idea of variables to hold values which our TensorFlow program is going to update during the training process. And along the way, we'll also use TensorBoard to visualize our computation graph, and we'll see how this can be done in a nice fashion by making use of named scopes. Let's start with linear regression. Let's use linear regression as an example because it is maybe the simplest machine learning problem out there. The basic idea of regression is to measure or quantify causal relationships. Given a statement like x causes y, we have two variables x and y. X is the causal or the independent variable, y is the effect or the dependent variable. This relationship between x and y is going to be quantified in the form of a straight line. That's the whole point of linear regression. Take an idea like this one, that wealth increases life expectancy. This is a hypothesis which we might want to test. Here we are saying that the cause is the wealth of individuals and the effect is how long they are expected to live. Linear regression would be used in a situation where this hypothesis is true and where the link is linear. So, increasing the wealth by 1 unit, whatever that unit is, will also cause the life expectancy to increase by a proportionate constant. This linear relationship between cause and effect is captured by linear regression. In a little bit, we'll also discuss other types of regression, such as logistic regression. Another example of regression could be a hypothesis that home prices fall as one moves away from a city center. So, the causatory variable here is the distance in miles from the city center, and the effect will be the price per square foot of a home. And once again, linear regression only ought to be used if we already have a reason to believe that there is indeed a linear relationship between x and y. In general, the idea is that x, or the cause or the explanatory variable, does not depend on y, but y depends on x. And that's why we will be able to represent these in a two-dimensional frame, assuming that there is only one x variable. We can do so by plotting the x variable on the x-axis and the y variable on the y-axis. Notice that this is only possible in two dimensions if we have only one x variable. In multiple linear regression, we will need more than two axes. That is called multiple regression. In any case, let's now see how a linear relationship would be found. Given data for a large number of homes, given the information about how far from the city center they are, and also about their price per square foot, linear regression is the procedure. It's an algorithm which will try and find the best straight line to pass through all of these points. And we'll get back to the definition of best in a moment. The key insight here is that regression line is a line. It has an equation of the form y is equal to a plus bx. And hopefully, this immediately signals to us that this is a use case for machine learning. Because after all, the regression equation, the values of those constants a and b, are going to change on the basis of the data points that we consider. Any machine learning algorithm changes its output, changes its parameters based on the corpus of training data, and our regression line satisfies that condition. And this is why regression is indeed the simplest example of machine learning possible. Now, it also turns out that linear regression is an example of the simplest function that can be learned by just one neuron. We'll get back to that idea in a little bit. Let's keep going with a brief exploration of simple regression. In simple regression, we need to find a line of the form y is equal to a plus bx. Given all the x and y coordinates of all of these points, in an ideal world, we would want to find just two constants a and b such that all of these equations on screen now are perfectly satisfied. In other words, in a case of perfect linear regression, The same two constants a and b ought to be enough to predict the value of y given any value of x. That's what this set of equations represents. And this boils down to finding the best regression line. Now, the question that's sure to arise is, what is the best line? What is the best fitting line? To make this real, let's consider a pair of lines y is equal to a1 plus b1x and another line, line 2, y is equal to a2 plus b2x. Let's compare these two lines. Visually, it's pretty obvious that line 2 is not a good fit. It's nowhere near the points which we are seeking to fit. But the question is, how do we mathematically express that intuition? How do we know mathematically that line 2 is not as good as line 1? This is performed using a procedure called minimizing least squares. But before we talk about the MSE estimation method to find the best values of A and B, I'd like us to first focus on the significance of the coordinates A and B in each of these lines. You might remember from high school coordinate geometry that it's possible to express the equation of a line in something known as the slope-intercept form. That's exactly what we've done. The line 1 has y-intercept a1 that measures the length or the distance between the origin and the point where line 1 meets the y-axis. That explains the significance of the constant a. Let's understand the significance of the other constant b. Given any pair of points on this line, what the second constant b tells us is, if x increases by 1 unit, how much is y going to change by? Notice here that these lines are downward sloping, and so we can interpret the slope as follows. We can state that if x increases by 1 unit, y is going to decrease by b1 units. We can go ahead and calculate this exact same set of quantities for the second line using the constants a2 and b2. Okay, let's now turn our attention to defining the best fitting line. And it turns out that the best fitting line is that which minimizes the least square error. The least square error of what, you ask? And the answer is the least square error of the residuals. Given a set of data points, the residuals represent those dashed lines which you now see on screen. These are the differences between the actual and the fitted values for each line. So given any candidate line, whether it's line 1 or line 2, we can find the residuals with respect to that line by dropping vertical dashed lines from each point to the corresponding line. The best fitting regression line is that which minimizes the sums of the squares of all of these dashed lines. And this now helps us to quantify our intuition. It's pretty obvious that the residuals or the dashed lines to the second line, line 2, are really long. They are much longer than those to line 1. And this explains why line 1 is the best fitting line. It's because it minimizes the sums of the squares of the lengths of all of these dotted lines. This is the theory of linear regression. Those dotted lines, which are the residuals, need to be as small as possible. And that sum of the squares is called the error. Now, this is bringing us very close to a machine learning implementation, because what we would like to do is set up a machine learning algorithm which calculates the values of A and B such that the errors are minimized. The way we are going to accomplish this is by starting with some initial estimates of the values of A and B, then finding the errors of a regression line defined by those estimates for our data points, and then feeding those errors back to reduce the values of those errors by updating the values of A and B. And when this process ends, we will have found the best fitting line using a machine learning approach. Let's return to the question we posed at the start of this video. Now, to be really pedantic about this, linear regression is none of the above, because linear regression is a problem rather than an algorithm. Linear regression is a problem which seeks to fit a line through a set of points. That said, linear regression can be solved using a machine learning approach, and to that extent, it can indeed be represented or solved using machine learning. It is not a representation learning algorithm, because representation refers to the case where the algorithm picks up on its own what features are important. It's also not a deep learning algorithm, at least in the sense of the common usage of the term deep learning, because we do not require a multi-layer neural network in order to solve it or to reverse engineer this problem. So technically, linear regression is a problem. It's not an algorithm, but it can be solved using a traditional machine learning based approach.